Dr. Diana Chow is the Paula and John J. Lavoie Endowed Professor in Drug Discovery and Development, Professor of Pharmaceutics, and Director of Institute for Drug Education and Research at the University of Houston College of Pharmacy. Dr. Chow has expertise and experience in IND-enabling preclinical studies, including PK-guided formulation development, PK/PD evaluations, and modeling in preclinical and clinical trials. She serves as the PI/PD of the NCI P20 program, partnering with Dr. Marty Matzik at Baylor. She's also a PI of subawardee of the CPRIT PK/PD and formulation grant that I was just discussing.
Have an overview about capacity and services doing the PK/PD modeling, and also show you a few cases about PK modeling and simulation and PD modeling, as well as the PK/PD correlation. Lastly, I'll touch upon lightly about the aromatric scaling. This is the slide from Don. Our portion is here. Can help to for experimental design and do the modeling and simulation, also PK/PD correlation. And this slide a little bit busy, just indicating the 4 different areas so we can provide services. However, I would go into individual cases, so you don't have to try to read those small font here. Okay, for PK modeling, because the CPRIT funding, we collect quite a number of softwares, and some of them we have very long-term experiences with, and a few like DILISIM, that's a new one we just acquired last year. So I'll just show you a few examples, talking about co-modeling of parent and metabolites, and also co-modeling can be from central compartment and peripheral organs. And this just is showing the profile. Probably Dr. Leong mentioned an industry standard use non-complementary analysis for its convenience. However, some profile you can see actually cannot describe the terminal phase. So that's how in our unit we focus a lot on complementary analysis. And this is the example Dr. Leong also mentioned about microphenolic sodium salt, IV, oral, and patch. You probably recognize the y-axis, the concentrations in the blood, very low from the patch, which is the intended. You don't want to get into the circulation. But from IV and oral, we recognize the second peak, and there's a patch, there's another one. Okay. And this is the model we developed. For IV, the small peak, we attribute that because this is study with metabolic cages. Therefore, the second peak is more likely internal enterohepatic recycling. If you don't use metabolic cages, animals tend to chew the feces. There may be another dose, but this is not the case here. So that's how we developed this model. This is central compartment, for peripheral compartment, and eliminated. And this drug from the circulation can also get to the bile and transfer to the gut and reabsorb back. That's what we are referring to enterohepatic recycling. And for the oral and patch, that involve absorption phase, so we add this. However, we recognize the rate constants among those will be different from different routes. Okay. And this is another one talking about CPT-11 and SN38. This is after dosing from the circulation, we can monitor both CPT and SN38. This is active moiety. And also, we recognize there's a second peak. This one has been published, so we could do the co-modeling of CPT-11 and SN38. And also, that would characterize all the conversion rate constants and transfer rate constants. This is another one, also PK modeling from our student's dissertation. This is for the clinical trial of riluzole, which is approved by FDA for ALS. But based on the mechanism, we find that maybe be useful in the spinal cord injury patient acute phase. So we have done we finished phase 1, partnered with Dr. Grossman of Methodist. And in phase 1, at that time, this treatment is for 14 days, 2 weeks. Clinically, they define 2 weeks acute phase. So they do the treatment for 2 weeks. So we are partner for pharmacokinetics study. They are thinking originally designed to take the last sample of 14 days to see what to confirm that exposure. But at that time we thought, based on the half-life, day 3 maybe we already reach a steady state. Therefore, we also suggest to add 1 point on day 3. And then to our surprise, the concentration did not stay. Instead, the concentration on day 14, day 3, day 14 is significantly lower than day 14. We don't know why, however, they're consistent among all the subjects. So we have done a lot of PK modeling. And in the phase 2 currently ongoing, we add a day 7 and day 10 sample. Because we like to know that decrease, because that decreased concentration we derived is due to the increase in bond distribution, increase in clearance. Okay, so we don't know whether that's a rapidly drop and then stable for those 14 days, or it's linear declination, or it's exponential. And with this phase 2 data together, we found that's exponential. So this is the model we developed, and this is a simulation to project, and the clinical sample in phase 2 fit in that model. Okay. This is student dissertation. Okay, now we also move on to enterohepatic recycling. This is CZ48, which is a lactone stabilized CPT. This is a very interesting project because we involve preclinical and clinical. We have learned quite a number of lessons from this. And this drug also have enterohepatic recycling. I'll give you the conclusion up front and then show you the data. Okay, this is a very good example showing that if we have thorough knowledge of PK from the preclinical study, that will help us to interpret the clinical unexpected observation. Also can help us to guide whether we need to have formulation, dosage form formulation. Okay, this is, we also developed that PK model with enterohepatic recycling components. We found that later, actually in the animal, we recognize the fact, but it's not a major one. However, later surprised us in the clinical trial that enterohepatic recycling is a major factor to convert the prodrug CD48 to CPT, the active moiety. I'll show you the information. Okay, this is just a CD48. This is lactone stabilized derivatives in vivo that were hydrolyzed into the active form, CPT. If you're familiar with the CPT, the lactone form is essential, but in the physiological pH, the lactone form will open as carboxylate form, which is inactive and responsible for some side effect. So if a dose of CPT, the half-life is very short, okay? And this is a prodrug. We continuously liberate that CPT and provide the lactone form for a sustained period of time. So the early 2000, one of my students graduated with the CD48 given by IV and oral, and showed that the IV declined very rapidly. IV is decline with reasonable degradation. However, the oral route have very sustained level. Apparently, different route administration, they behave very differently. And then we monitor the CD48 total, CD48 lactone form, and CPT lactone form, which is the active moiety, also sustained. Okay, so at that time, we thought very likely there's enterohepatic recycling. And later, another student studied intensively the biliary excretion of CD40 and CPT after oral and IV doses. With the IV dose, we recognize in the bio, mainly it's a CPT, significantly higher than CD48, and roughly 3% of dose. We also do the pharmacokinetic analysis and know the clearance from the bio to the bio significantly higher with the CPT. And also we recognize usually enterohepatic recycling is referring to the conjugate. But this time we found that CD40 and CPT, they secreted into bile as a parent form. That's not originally anticipated. So that's only 3% of dose or 3% of clearance into a bile. So that's how we conclude that in that rodent it's not a significant route. But also we do that oral route. It's very interesting to see in the plasma, it's a CD48 significantly higher than CPT, but in the bio it's mainly CPT and much lower of the CD48. This is IV and oral, okay? But this is the bio. Okay, bio is a CPT, significantly higher than CD48. And this is how we learn from that preclinical study. They secreted as a parent form, and CPT is a major species to be secreted, and only about 3% of the dose gone through that enterohepatic recycling. And then that CD40 is moved to a phase 1 trial. It's still ongoing. And in the early part of the screening, that's a screening of patients with a blood sample for up to 48 hours after single dose. And then later initiate the clinical trial, multiple dosing. Okay. But this again a conclusion up front. Okay. We found that we build up the model based on the preclinical PK. We can project the CD48 very well, but not CPT. And CPT showing significant accumulation for a long period of time. So this is our base model, the co-modeling CD48 and active moiety CPT. Okay. And this is a base model based to simulate CD48. It reaches steady state, about 4 to 5 half-life of the compound. They all fit, all the measurements during the treatment, they all fit in well, okay? However, the 2 slides to show you, that's an observation for CPT, okay, the red dot. And the blue curve, that's a simulation from the base model. What do you recognize? Most of them, the model underestimate the exposure. Only 1, and this 6. The next slide, another 5. What did you find? Most of them, the model underestimated the observation, the outcome. There's a few more still close. So immediately we thought about the preclinical knowledge about the PK. So we just move on to modify the base model by adding the enterohepatic recycling component. And some of them, because the recycling, that's how CPT can sustain and remain high. And some of them is not that much because they secreted the bile, half a recycling, but also eliminated from there. Okay, but they are the same model with the component. Model B and C. So as a result of that, all the subjects, based on the screening profile, we can project all those profiles, except 2 of them. This is a overestimate and this underestimate. We also recognize from screening to treatment, those terminally ill patients, pathophysiological condition may affect the PK. Okay. However, this example In the early phase of phase 1, we received the FDA holding until we convince them we have the model, can project and know how to adjust the dose. And that's lifted. So it's still ongoing, almost finished phase 1. And also from this, we learned that phase 1 is supposed to dose escalating, but actually based on the CPT profile, there's no need to increase the dose. Actually, probably downscale that. So that's a lot of enriched information we can derive from there. Okay. Okay, for PD modeling, we have those softwares. That's methamphetamine, very worthy. We probably just call DEX. This study partnered with Texas Children. That's we give a dose, and this is you and fetus. We monitor the PK in maternal as well as fetal, and also have a PD management from the hospital. And this is a PK presentation has been receiving awards in those national meetings, but this is not the most successful PD information. Okay, this one talking about the blood pressure and heart rate in the maternal compartment. That's a free concentration in picogram per ml, and this is increase the dose, only slight decrease in that PD. That's probably the dose already reached high in that species. And this in fetus, what we learn is pretty unpredictable for this. Okay, the exposure definitely much less than in the maternal compartment. But this is how usually we would correlate PK/PD. But at least recognize this limitation. But that project already over, so we cannot rerun. So this is the part we haven't published. Okay, now we get into the PK/PD correlation. We have different models, softwares available. And we're going to talk about, this is not a cancer project, cancer research project. We're talking about a statin PK/PD in gastro bypass bariatric surgery. That's a partner with the Methodist Dr. Sherman. Because for bariatric surgery, this gastric and intestine has a major reduction. There's in literature not clear how would that impact PK, the body handle the drug. So this is the one student already graduated from this project. The PK/PD modeling, we have a PK and also have a PD. PD is talking about exposure and response. Probably when you study pharmacology, you learn that dose response, but in our PK's point of view, dose cannot relate that well. So exposure actually get into the circulation. And combine those two, actually PK/PD works hand in hand. We can construct a model, relate the effect of what's the time profile of the effect. And also we can relate what's the exposure, required exposure for efficacy, and what would the exposure need to avoid for toxicity. Okay, this is for those clinical trial. The subject monitor baseline and 3 months, 6 months, and 12 months after the surgery. And this is the LDL concentration versus the total concentration of statin. Because in our LCMS MS assay, we developed the assay can monitor statin and also 2 active metabolites. So we correlate the effect, the decrease of LDL related to the concentration. What do you recognize among the 3 curves? Different period post-surgery. There's a different PK/PD correlation. Okay. So that's how we thought, other than this is effect versus exposure, we add another parameter, the BMI. After surgery, there's a change in BMI. That may change the drug. Originally we thought only affect drug absorption, but actually later we found that with the assay we can monitor metabolite. We found also affect metabolism, also affect distribution depending on the nature of physical chemical nature of the drug. Okay, so with this one is also software in our Design Expert 11. we use this. Actually, this one originally purchased for developing for systematic development of optimized formulation. Okay. We also have that, which show actually LDL affected by the total concentration of atorvastatin and the two metabolites, also affected by BMI. Okay. So therefore, we would know the given BMI and given exposure, we can project what will be the LDL. And also, if we know what's the target LDL, we know that what kind of exposure with the given BMI. And this is show the correlation. There's different colors, different group. Okay, for PK/PD modeling, I'll just give a few slides of the theoretical portion. That's an empirical model. But nowadays, more and more towards a mechanistic model that probably will have a better prediction. And for mechanistic, also have a direct link or indirect link. And for chemotherapy, often it's irreversible. And this is just one example showing you can have a PK, you have a complete profile, later you can have few points, and you have PD measurement. Ideally, whenever you have blood sample for PK, you do some PD measurement, but sometimes it's not feasible. Sometimes we're given the data already been performed, but still, if we have a PK idea, we can project what will be the exposure at the time point when PD was measured. And that's a more complicated of an indirect that shows the distribution delay to the site. So that's indirect effect. That those software have the capability to do all this. And this just showing that some of the PD have a baseline measurement. That's a full sigmoidal Emax model. And some of them, they don't have to begin with. That's a fractional. And it just showing that we have those software can handle all this PK/PD. And just show you a few. This one, you don't have that. Well, then it's difficult for you to read because if in the bottom you have that, you can enlarge it in any portion. But that one just show, just take my word. So if your measure have a GastroPlus have the capability to be an ADMET predictor, also can do the PK modeling, to the PBPK modeling. PBPK physiological based. So if you have preclinical data involve disposition of the drug in different organs, that you can apply this, and also that would project the drug-drug interaction. And maybe it's safe towards the end. I know somebody asked a question about between the GastroPlus and Simcyp. What's the difference? I have the answer when we get into the section. Another one, that's a new one, as I mentioned, a new toy, Dilasim. That one is drug-induced liver injury, okay, especially for nanoformulation. Nanoformulation is uptake by RES, liver, okay, spleen, and lung, several of them. They will tend to accumulate those nanoformulations. So if a biodistribution study showing accumulation in those sites, especially in the liver, if that's not intended site of action, we definitely would like to explore what's potential for this risk. Okay, and this is just we know the PK, the exposure information in the circulation as well as a different organ, and then also know that for the in vitro work, many mechanistic study showing the mechanisms of action that have potential to damage. That's in this area. So also we have the intersubject variability. So the software can group those together, integrate those together to make some preliminary projection. Okay, we haven't had the data to show using this. But for a new compound, if the distribution in those IES systems, especially in the liver, this is what we recommend to go through. Okay, the last one, allometric scaling, because often the preclinical involve FDA require one rodent species, one non-rodent species. But often in our lab, for example, Dr. Liang's lab capable of doing rats and mice. If you have those two sets of data, we can initiate some allometric scaling. Allometric scaling, the principle is, that there's a log linear relationship between pathophysiological parameters and body weight. And the pathophysiological condition, many of them related to PK processes. So that's a PK parameters related to this. So we just recognize those constant, it's not dimensionless, depending on which property we're dealing with. And the B is that aromatic exponent, often less than 1, but sometimes also will be different from this value. It's locked. Locked. Okay. Yeah, this is just showing different set of those variables. For example, those physiological variables, surprisingly, the log of those property related to the log of body weight for most of mammals. And those relate also with affect the different pharmacokinetic parameters. So based on that, we can, based on the animal data in rodents and non-rodent, can extrapolate to human at 70 kilograms. This is showing that there's a linear relationship. So if whatever the PK parameters for different species have different value, generate this relationship. And with the 70 kilogram, that will be the projected parameters in human. And this few slides just showing what we can do with aromatic scaling and the tox, the scaling. We can rationally select first dose in human if there's a brand new compound. And also, we can use that to extrapolate parameters from from animal to human. And in clinically, we can extrapolate these parameters in adult to pediatric population. And also, that can extrapolate from the normal subject to obese population in terms of pharmacokinetic parameters. And also tox endpoint into human. And also from there, plus the exposure correlation with the PD, we probably can more rationally suggest what will be the dosing regimen in human. And this is just a few steps we will usually do with the different species to do the PK analysis, and then establish that relationship, log linear relationship. But when that exponent deviates from that one value, sometimes we have to adjust with the brain weight of the species or fraction n-bound or maximum lifespan. Just like a 70 kg human and 70 kg of another animal, they may be different because of those factors. And extrapolate the parameter value to 70 kg human subject. And use that to predict the pharmacokinetic parameters in human, and also project what will be the exposure. Then the first study can confirm, validate that model. That's probably all I have. Oh, okay. And the observe PK compare with the projected value. So this is to refer back to the first slide. That's all 4 areas of our services and capacity.